Namaste. Myself, Sachchida Nand, Assistant Professor, Department of Mechanical Engineering, Buddha Institute of Technology. Today, in the continuation of materials engineering and the continuation of atomic structure of material, we are reached to study the various crystal structures as we discussed earlier in the classes also, as well as how these structures playing a vital role for maintaining the property of the structure. So, we will discuss these things. As in the earlier classes, we have discussed about the atomic structure and the crystal structure. So, in that continuation, I am going to present, or we are going to discuss the detailings of the crystal structures, and leading to that, we will reach to the points on that these particular crystal structure behaviors and the role of that particular atoms in that crystal structures with the help of various kind of defects. That defects which particular leads to maintain the property of the particular material, that material's property which sustain that material for maintaining the working environment condition for a particular product. So, for that we are discussing that first we need to study, or we need to discuss that what is the crystal is all about. So, as we discuss about the unit cell, that the repetitive mode of that particular atomic arrangement, that is the unit cell in a repetitive manner, that is defined by the various structures, cubic, tetrahedral and octahedral and different kinds of structures we discussed earlier in earlier classes. So, here we go with the crystal, the lattice, the where to repeat, as we discuss about the lattice, the space between the atoms and arrangement of the systematic arrangement of the atoms, that is also linked to the unit cell of the particular material, the unit cell of that particular arrangement. So, the systematic arrangement of the atom in a unit cell, that is particularly defined by all these things. So, the crystal where to repeat and what to repeat, that is the lattice plus motif. That the unit cell of the BCC lattice, as we discussed about the BCC body centered cubic, that all the atoms are arranged in a cube at a corner and one in the body's center. So, that is how it is defined as the body centered cube. And that crystal is also linked the space group, that is how it repeats, and that asymmetric units, what to repeat. That what to repeat and how it's repeat. The how it's repeat means the particular cubic section is repeating, and how what is to repeat, that is in the manner which that thing is to be repeated. So, the progressive lowering of symmetry among the 7 crystal system, as we discussed about, as I already told you, that is the cubic, tetragonal, orthorhombic, trigonal, hexagonal, orthorhombic, monoclinic and triclinic. These are in the increasing symmetrical way, and these arrows mark lead from the supergroup to the subgroups. So, these as you can see, these particular marking of that particular you can say arrows are telling that particular how that system is arranging, that crystal system is arranging from one to another, that is leading to from one where and what. So, if we are talking about the cubic crystal, how it look like and how it is to be. So, these are the things which we discussed in the earlier classes, the arrangement of that particular, the A is equal to B is equal to C is and that is alpha, beta and gamma is equal to 90 degrees. That is how that particular symmetric of that particular crystal structure is showing, and that is a simple cubic. If we consider the simple cubic, that is containing the two kinds of structure, that is the cubes, that is the BCC and the FCC. That BCC leads to the body centered cubic I, which is denoted by the I, as you can see, and another is the face centered cubic FCC. So the point group are the 4, 2, 3, that is the arrangements of that it is like. As you can see, the others are also showing in this particular figure, that is the tetrahedron, that is showing here that particular arrangement, and that pyrite cube is showing that particular structure, and then garnet, the dodecahedra, and the fluorite is octahedra. So that is how these particular structures are made, and the arrangement of that particular is lead to the solid materials. So crystals and the properties, these are in the coexistence. As you can see in the previous classes also, the structures are related to the properties. So the symmetry of any physical property of a crystal has at least the symmetry of the crystal. So the properties of any crystal is the symmetry with the crystals, that the arrangement of that crystal and how these are arranged, and that is the arrangement of that particular structures leading to the various properties of that particular materials. So in the next point, the crystals are anisotropic with respect to the most properties, and the growth shape of a well-growth crystal has the internal symmetry of the crystal, that is the arrangement, the unit cell arrangement. So polycrystalline material or aggregates of crystal may have isotropic properties, that due to the averaging of many may randomly oriented grains, and in the similar, the property of a crystal can be drastically altered in the presence of defects. So these defects are basically that particular plays a very vital role. We will discuss all by the step by step how these particular defects. First of all, the things defect word come to our mind, that is totally change the scenario. Defect means that is the defective piece, but that defect it leads to the various property of that particular material in this particular scenario. So this is all the classification according to that particular, the classification of defects based on the dimensionalities, how they are arranged themselves. So 0D, that is a zero dimensional, that is a point defects. It is categorized, that defect is basically categorized in these scenarios, that is the point defect. And second is the 1D, the line defect. So third is the 2D, that is the surface interface, or you can say surface defect, and 3D, that is the volume defects. So these all are defined by these particular points. So we will discuss one by one how these particular defects control the structure of that particular material, and that structure lead to the various property of that particular material. So these all are related to that, and that is how these particular materials are behaved. So first we will discuss about the 0D, that is zero dimension, that is a point defect. As it is clear why that is that the thing is hidden in that particular, that is that point. It means that is there is some defect in that particular location, that some we will discuss in the later classes, that is the arrangement, that is some missing point in that particular crystal lattice. So that how we will discuss, that is how it all defined. So that is the absence of particular point defects. So how it work, and that the point defect, that is showing the arrangements of that particular atoms in a systematic manner, and from there is a one missing part of the atom which floating from one place to another. So we will discuss how these things are happening. So non-ionic crystal, these are categorized, these point defects are categorized in two categories, the non-ionic crystals and the ionic crystals. So first we will differentiate the non-ionic crystal, that is the vacancies and the impurities. As it is clear from its name, vacancies means the vacant place, impurity means some impurities included in that particular structures. So impurity means that is the another particle, or you can say another substance of another material included in that, and they are categorized in two categories, that is the interessential and the substitutionals. So how these are working, we will discuss by the graphics, how it works and how it helps to produce the various kind of structures. So as we discussed, that is we are combining the two materials, and they are combining their atoms attracting each other, and they combine with each other, and there is how they are improving their properties. So these particular defects are playing that point of role, a very important crucial role at that point of the mixing of two materials. They are providing the space, they are providing the impurity, they are providing some kind of space to adjust that another material in between their crystal structure, to maintain the balance and to create the structure which leads to the various properties. So that is how these particular defects play a very vital role. So second one is the ionic crystal, that is the Frankel defect and Schottky defect, and related to the others also. So these Frankel and Schottky, you can say the sum up of that particular non-ionic crystal structures, how we will discuss in the next slides. So imperfect point, like the region in the crystal about the size 1 or 2 atomic diameters. So that is how this particular imperfect is defining. So as I told you about the vacancy. So how the vacancy means? The vacancy is the vacant place. So there is an arrangement in the unit cell, or you can say, you can see here, there is a unit cell. If you consider that particular thing, that particular unit cell, right? So all the atoms are arranged, but one atom is missing. That means that it creates the vacancy, and that is how the other materials came here to adjust themselves. So, but this is not the point to be considered right now, but I am just telling you that is how, what is the vacancy is all about. So missing atom from one atomic site, that atom around the vacancy displayed, the tensile stress field produced in vacancy means that but as we know, the atoms are charged and they are moving from one point to another, the lower from higher state to lower to higher state in their certainty, and that how what is happening particular thing and how it happens, that is the flexibility which are arranged in that particular atomic level when we are applying the tensile strength. Tensile strength means we are applied the opposite direction force on a material, like we have a kind of you can say that is the we have simple I don't have some kind of material, like we have this particular thing, I have these things. So I am applying this particular load from this side also, this side also. So what is happening? There is a stretch in between them. So this particular stretch provide another kind of energy, which is ignite the particular you can say the interatomic energy of that particular atom, and that is how that particular atom move from one place to create a kind of a vacancy. So this is just a one condition, that is how it works. But in the scenario, in the mean, if we are talking about during the making of that particular, that the atom have the tendency to move from the higher to lower state and lower to another state. So because of their charge, and that charge is help to create that kind of tensile strength in the material, and that leads to the ductility of the particular material. So that is how these all are combined with each other. So as you can see, we talked about the vacancies. Now the impurity is called the interessential and the substitutional. How they play the very vital role. You can see here in the figure, that particular figure is showing that the interessentials, they are taking the place in between. That suppose we are sitting in this particular chair here, in this particular chair only 10 persons are allowed to sit. So if 11 persons are need to be set, how it will adjust themselves, either sitting in the legs of others, or just remove another person. So either they can adjust themselves to maintain that particular person, and that is how the atoms are making their space in between them to involve another materials atom in between to promote various kind of properties. So that is the relative size and the compressive stress field, where that particular another materials are adjust with that particular materials. As you can see, this is the compressive field, this is the tensile field, which particular providing that particular things. As this particular, this is the thing is the during that particular tensile loading and the compressive loading, how it works when we are applying that particular loading or not, that particular structure have a tendency to work according to that particular tensile and the compressive load. So substitutional impurity, the foreign atom replace the parent atom in the crystal, means if we are making an alloy, means that we are combining it. For the example, copper is sitting in the lattice side of FCC nickel. So that is the thing which we are discussing for the substitutional. We substitute from their particular things by the another thing, that is the substitutional. And the interessential means they are imbalance between them. The foreign atom sitting in the void of that particular crystal, that they have their space, and in this particular very less space, that another material involve themselves into that particular location to create the different kind of a property. So for example, carbon is sitting in the octahedral void in heat treatment, that is the HT-FCC ferrous materials. So that is how that particular metals are combining each other, and after combining they are creating these kind of structures, and that structure lead to that particular properties of the materials. And that's why these particular defects are playing the role. So you can see now, and now you are going to, you can observe how the defect word is real mean in this particular scenario. It doesn't mean that it harm that particular atomic structure, but it involving that themselves in that particular atomic scenario to enhance them, their arrangement and enhance their property in this particular scenario. So these are the particular examples which are showing here, that is the R octahedral void and the R divided by R FCC that is the atoms. This is a 0.141, that is the difference between them, and that is how these things are combining themselves, and that's the solubility limit of 2% of weight, that is the 0.923 at percentage. That is how the interessential carbon sitting in the octahedral ferrous FCC structure, because of their interatomic bonding, because of their interatomic spacing, how they are creating their space, the carbon creating their space in the compressive strain, and that is how they involve that particular iron, and after involving themselves they improve their particular hardness of that particular material. So interessential carbon sitting in the octahedral void, that is the LTBCC ferrous, that is how it's replacing all these things. As you can see from the particular slide, that particular is showing in the BCC structure, that is how they are arranged themselves in that particular energy scenario. And but the C, that is the carbon sit in smaller octahedral void displaces the fewer atoms, so that the particular difference between the FCC and the BCC structure, where the carbon is taking place themselves in that. So these are the equilibrium concentration of the vacancies. That vacancies, the vacant space of that particular atom in that space lattice, or you can say the atomic structure. So the formation of a vacancy lead to the missing bond and distortion of the lattice. That the things we discussed earlier. That is the thing we are discussing throughout this particular points. That is the missing of the bond or the distortion of the lattice. That is how the particular one atom is removed from that particular lattice. So the potential energy, that is the enthalpy of that particular system, is increased as the particular system is removed from that position. So work required for the formation of the point effect, that is the enthalpy formation, that is the kilojoule per mole. And though it costs energy to form a vacancy, its formation lead to the increase in configuration entropy. So above the 0 Kelvin, there is an equilibrium number of vacancies. So that is how these particular crystal structures are having these things and explaining all these things. And this is the gives free energy system which shows that particular number of vacancies which are including here, and that is how this concentration graph is showing the perfect crystal. From there the concentration, and from there the equilibrium to the concentration level. So taking place, the certain equilibrium number of vacancy are preferred to the temperature is 0 greater than, that is the T is 0 to Kelvin, and the vacancy play a role in that, the diffusion, clamp, electric conductivity, creep, etc. And that is how this particular property of the metals or the materials happen. Now we are moving toward the 1D, that is the line defect, and that line defect is the improved version of that vacancies. That is the point defect, that is the shear module that is showing, which is a particular thing showing the dislocations, that is the weaken the crystal, and that is how that particular dislocation is defined. These are defined by the edge dislocation, mixed dislocation, and the screw dislocations. So the usual dislocation have a mixed character, and the edge and the screw dislocation are the ideal condition, and these are the extreme. That is how the dislocation of that particular atomic arrangement from one place to the another place, it is shifted in the circular manner or in the particular manner, how they are traveling from one place to the another place in their particular crystal structure scenario. So the motion of the edge dislocation, that this movement of that particular, that as you can see, this is related to that particular 0D also, that is the movement of that particular atom from one place to another, which also lead to that particular things. That is the conservative and gliding motion and the non-conservative clamping motion. These are the two conditions by which that particular edge dislocation is defining, by the gliding or by the clamping. Okay, so the motion of dislocation on the slip plane, that is the motion of dislocation perpendicular to the slip plane. So for the edge dislocation, that is the B is perpendicular to the T. They define a plane that is called the slip plane. They slip from one place to another or shift from one place to another. So the climb involves addition or subtraction of the row of the atom below the half of the plane. That is, a positive climb is equal to climb, that removal of the plane of the atom, and negative climb, that is the climb down, addition of the plane of the atom. That is the increasing and decreasing. That the system which I am showing here, that the increasing in this particular one way, and when it is shifted, that is the shifting. That shifting, that is the first, is the perfect one, that is in the inline, and that is the shifting. So that is how that particular things are happening, as you can see in this particular figure, that the particular the system, that system is shift from one place to another. That system is free from there. So there is the space, that the shift which is related to that, and that is how this particular figure is showing according to that particular reason. So that is how this particular mixed dislocation is showing, that is the pure edge dislocation and the pure screw dislocation. That pure edge dislocation you can see here, that is the shifting of that particular plane from one to another, as this plane is shift to this angle, and this is the screw, that is the shift from that to that level. That is the increasing of that things. So the role of the dislocation, how that particular role, that dislocation invent the particular properties of the material, and that is why we require this kind of deformation, this kind of defects in a material structure to provide a various kind of properties, that is the fatigue, creep, fracture, slip, and the diffusion in the pipe, that is the structure, the incoherent twins, the grain boundary, the low angle, semi-coherent interface, the disk of the vacancies, and these creep mechanism across the slip, dislocation, climb, vacancy, diffusion, grain boundary, sliding, and these all the things. So role of dislocation play, that is the deformation process will happen in that particular materials. Now the 2D surface or the interface dislocations. So the grain boundary region may be distorted with atom belonging to neither crystal. The thickness may be of the order of few atomic distance. The crystal orientation changes abruptly at the grain boundary. In and low angle boundary, the orientation difference is 10 to power 0. So these, before proceeding all this scenario, I will go to that particular slide also, that is how these particular things are combining these things. So as you can see this particular slide, so that is also showing the dislocations of that particular, as you can see that particular things, that particular line is missing here, that particular line is missing here, that arrangement is missing here. So that shifted from one place to another place, that is shifted to here, and that shifting leads to that particular thing, and that is how the grain dislocation is also taking place, and how these things are taking place as we will discuss. The grain boundary defects that lead to that particular defects. So one defect is related to another, another is related to another, and that is how these particular defects are playing the vital role in the creating of the structure and the properties of that particular materials. So in a low angle boundary, the orientation between that is less than 10 to power 0, and the low angle boundary, the distortion is not so drastic as the high angle boundary. So that the things to be considered in the grain boundary defects, and this can be described as an array of the dislocation. That array, that is the arrangement of the dislocations, you can say. So the grain boundary energy is responsible for the grain growth or the heating, that is greater than 0.5 pm. The large grain grow at the expense of smaller ones. The average number of nearest neighbor for an atom in the grain boundary of a closed packed system, that is 11. So this is the figure, you can see that is the zoom figure of the 10 micrometer of the mn, that is the grain boundary showing of this particular material, and that is how these particular things are notable here, as you can see how these grain boundaries are taking place and how these grain structure are taking place. So the types of boundaries, that is the grain boundary between the BCC crystal, that is the energy level is 0.89, the grain boundary between the FCC, that is related to the 0.85, and the interface between the BCC and FCC crystal structure, that is related to the 0.63. Now this particular grain boundaries structures, as you can see here, that is the space which is locating here, showing the different particular points, that is the grain boundary, the region which are distorted from with atom belonging to the neither crystals, that particular things, which is that particular things, as you can see. So that particular leading to that particular twin boundary in the particular surface defects, you can say. So what is happening in these twin boundary defects? So the atomic arrangement on one side of the twin boundary is related to the other side by a symmetric operation, usually a mirror image. You can see that particular shifting of the plane from one state to the another state, that is the twin boundary defect, you can say. So the mirror image of that particular atomic arrangement is shown into that parallel condition, and that is how the twin boundaries are created. So that the first point is telling the atomic arrangement on one side of the twin boundary is related to the another side, that the similar operation is happening, that is the in front of you. If we are putting a mirror, you will see your face, and that is how this crystal structure is creating that the mirror image, that is how the twin boundary is known as, is called. So the mirror twin boundaries usually occur in the pairs such that orientation differences introduced by one is restored by the other, and the region between the regions is called the twin region, and that is how this storing of that particular pair differences that leading to the twin boundary, that is the, you can see that twin is defined, that is the annealing twin and the deformation twins, the form during the recrystallization. So annealing is the process of the heat treatment in which we are enhancing the structure, or you can say we are recrystallizing the structure of the material, and that is why the twins is happening, and that is why we are also required these particular types of defects in that particular material to enhance the property of the material. And that deformation twin, the form during the plastic deformation. Plastic deformation, you can say, when we are applying a kind of a mechanical loading on that particular ductile material that deform in that particular different locations, that particular if we are applying that particular thing in you can say in the forging operation, where we are hammering on that particular material, or we are stretching that particular material by after hitting on that particular things. So these are the materials, these are the processes by which these things are happening, and this particular plastic deformation is leading to that particular material that it will not regain its original shape. It will totally deform into permanent original shape, and that the stretching of that particular material by the help of that particular processes and is happening this kind of twin boundary in that particular structure, and that is how these particular materials are working. And this particular figure is showing the annealing twins in austenitic stellar steel. So that is the figure of a austenitic stainless steel, after which a twins part is particular, as you can see here, that particular twins, sorry, the cursor is moved somewhere, yes, here. So these particular regions, as you can see, the twins are happening over here. So the deformation twin, this is the things are happening, and this figure is taken by this particular references of that particular transformation of the metal, that is by the Paul G. Sharon McGill publication in 1969. Now the twin boundary in Fe doped SrTiO3, that is a bi-crystal artificially prepared. That is how we are basically creating all these things. So that's why we are studying the engineering materials, that we are doping that material, we are creating the material, we are disturbing the atom's structure, we are including the atom structure, we are changing their planes, we are extracting their surfaces, we are including the material by changing the scenario of that particular things, and that is how these things are happening. And you can see from this particular figure, that particular figure showing the high resolution micrograph, that is the micrograph mirror related to the variant of the twin plane. That is the figure taken place, as you can see from that particular figure. That particular figure is showing here. That is the twin boundaries are happened, and these are the very high resolution of the figure which is taking place, that the particular micrograph which are taken for that particular doping of that particular material. That is how material is introducing in a ferrous material to enhance their properties, and that is the figure taken by the Aspen, O'Kizel and Infant research paper, and that is they research in that particular material and created that kind of a boundary, and they dope particular material for creating these kind of things. And that is how we are creating a material, we are improving the material, and that is how we are enhancing the particular property of the. So as you can see from this figure, the twin boundary in the Fe doped SrTiO3, that material is doped, that is creating a kind of a new material, and that is how the twin boundaries are taking place in that particular scenario is discussed. So the grain size and the strength, how we conclude these things, how we examine these things. So that is OY is equal to sigma I, that plus K by root D. So sigma Y is the yield stress of that particular things, the grain structure, and the sigma I is the stress to move dislocation in a single crystal, the stress which we require to move that particular crystal from one plane to another plane, from one place to another plane also. So that K is the locking parameter measure of the relative hardening contribution of that grain boundaries, and the D is the grain diameter, and that is the Hall patch relation which is showing the grain size and the strength. That is how we are examining this particular size of that particular things. So these are the very minor level, at the micro level calculation is taking place in this particular scenarios, and that is how we are examining all these things. And after examining these things, we are we reach to that particular point, that is to examine all these things. So this particular relation is showing that the grain size and the strength of that particular grain structure to be need to find out. And furthermore, in the later classes we will discuss these particular things, that is how the defect further will be inquired, and these are the origin base which I just showing you. That is how we will enlarge, we will filter more and more this defect, that how these are the things is happening, these particular twins boundaries, and that is the particular vacancies and the role. These are the particular place in this particular tilt boundaries, and this is the particular figure of the tilt boundary, and which earlier we discussed about the particular twin boundary, how they shifted. That is the edge. This figure is from the edge dislocation which I am going to show here. That is the particular things which is happening here, that particular things which is happening here, and that is created by this particular figure. So that is how we will discuss all these things in the next classes, that how these are the climbing taking place, and that particular climbing is to be considered, and further the inquiry of that particular things to be made. So till now we will left this particular lecture for further inquiry of the defect, how to take how to study this defect in detail, to know the arrangement of the crystal structure and the enhancement of that particular property in that particular scenarios. So for that I am just putting this for now, and thank you.